Hello and welcome to this BitifEye tutorial. In this tutorial, we will show you the usage of our USB Link Training Suite software, the perfect tool to perform the initial debugging of the USB physical layer. This tutorial consists of two parts. In part 1, we will show the general usage of this tool. In part 2, we will introduce the expert mode features for advanced users to fine-tune the link training sequence and patterns. The tool is divided in two sections. The left section contains bus-specific parameters, USB in our case. The right section allows us to configure the hardware, voltage levels, jitter, etc. The first thing we have to do is to connect to the test instruments by clicking Connect. The connection dialog shows up and we can select between three options. Option 1 is the Jaybird configuration. The second option is the number of Jaybird channels to control, and the third option is a remotely controlled power switch to regulate the power supply to the device under test. In this tutorial, we will use an M8020A with one channel configuration and no power switch. We enter the visa address of the instrument and click Connect. Once the connection is established, the instrument configuration is fixed and we click Initialize Instruments. During the initialization, default parameters like the data rate are applied to the instrument. Now we configure the tool to match our DUT's physical parameters. For this tutorial, we will use a USB 3.1 device with a micro-B connector working at the Gen 2 data rate with 10 gigabit per second. In the next step, we configure the low-frequency periodic signaling. Clicking LFPS common shows a dialog that allows us to enter parameters that will be applied to all kinds of LFPS signals. First, LFPS burst period and duty cycle. Second, the type of signal used to represent electrical idle. In this case, we will use default values and the M8020A Jaybird squelch functionality by selecting M8020A idle. Next, we can configure the timing parameters of the superspeed capability declaration and LFPS-based pulse modulation signals, SCD and LBPM for short. Optional, depending on the duration. These signals consist of an LFPS burst and a portion of electrical idle. SCD signals have similar duration of LFPS burst and encode a logic 0 or a logic 1 by changing the duration of the electrical idle portion. LBPM signals encode a logic 0 or a logic 1 by varying the duration of the LFPS burst. Once we are done with the configuration, we click OK. Next, we can select the link training method that will be used to bring the device into loopback, the test state used for physical layer compliance testing. If warm reset is used, the instrument will send a warm reset signal to the DUT prior starting the link training. This method is supported by devices only. If power 1 reset is used, the DUT will have to be turned off and the link training will start as soon as the DUT is turned on again. The link training methods containing LTSSM work in a similar way, but make use of the M8070A interactive link training functionality. For this tutorial, we will select warm reset. After clicking Configure, a parameter dialog will open. That shows a partial view of the link training and status state machine or LTSSM. That shows a partial view of the link training and status state machine or LTSSM that focuses on the sequence of states and patterns required to reach the loopback state. In this dialog, we can customize the number of SCD1, SCD2, LBPM PHY capability and LBPM PHY ready messages, as well as the number and content of the TSEQ, TS1, and TS2 ordered sets used during the polling substates. Finally, we can customize the modified compliance pattern used in the loopback state by changing the number of CP9 blocks, the skip ordered set insertion rate, and the number of skip symbols within a skip ordered set. Once we are done, we click OK. Going to Instruments, Show Connection. Here we open a dialog describing how to connect the device under test to the instrument. It is recommended to use low-loss phase-matched SMA cables, which are available at BitifEye. We click Apply to transfer the configuration, link training patterns and sequence to the instrument. Going to Options and selecting Pulse Sequencer State will display the current link training sequence state on the test instrument. Now we will power cycle the DUT and click Manual Trigger to start the link training. The test instrument is now sending out the loopback pattern. We can confirm that the DUT is in the loopback state by performing a BER test. To do so, we first click on Start BER Measurement and then click on Analyzer Auto-Align to synchronize the analyzer pattern with the signal transmitted by the DUT. We now click on Reset BER Measurement and we can see that the DUT is indeed in the loopback state, receiving data and transmitting it back without errors. We can insert bit errors anytime to verify that the BER measurement is still running and reset it to show again that the DUT is error-free. We can modify the amplitude of the signal sent by the pattern generator by moving the slider. To synchronize again, we click on Analyzer Auto-Align. We will now add some periodic jitter to the generated signal to see how much jitter the DUT can handle. We click on Current to display the current BER status instead of the accumulated result. Now we click on Jitter, or SCC, enable the periodic and slowly increase the amplitude using the slider until we observe that the BER is greater than 0.0. We press the reset button to revert the value to 0. We press Apply and close the screen. Hope we were able to give you an idea about the USB solution. That's all. Thank you for watching.